Imagine a pendulum, like the kind you might find in a grandfather clock, swinging back and forth with a simple, predictable motion. Yet, when you attach a second pendulum to its end, order quickly gives way to unpredictability, a hallmark of chaos. But where is this unpredictable motion coming from? Could we find a way to extract order from chaos? And what does it look like at the strange elusive border between chaos and order? With the help of detailed simulations and eye-catching visuals, we'll dive into these questions as we discover the rich and surprising behavior of what seems to be a very simple thing: the double pendulum. Let's start off with a double pendulum. We'll label each pendulum's angle, and from here on out, we'll color the first pendulum yellow and the second blue so we can easily tell them apart. Now, let's duplicate it many times, raising the angle of the second pendulum by 1 degree with each new copy. Even though they start from nearly identical positions, can you guess how quickly they'll drift apart once we let them swing free? Alright, next, we'll reset them to their initial positions, but this time, we'll set the difference between one double pendulum and the next to just 0.01 degrees, a difference so small it's imperceptible. We'll line them up. And along with this perspective view, let's add a front view so we can get a better look. Okay, it appears even the tiniest difference in the initial positions leads to drastically different outcomes fairly quickly. For the last time, let's push this to its limit by incrementing the angle of the second pendulum for each new copy by a whopping 0.00000001 degrees. This angle is so incredibly tiny it's equivalent to, when looking up from the ground, how much of your visual field is covered by a tennis ball that's on the moon's surface. Or if you're American, picture a Big Mac that's 5 million football fields away. Oh, and for good measure, let's make 1,000 of them. To get a clearer picture of the simulation, let's slim down and squeeze the double pendulums together, slap a color gradient, and simultaneously observe them from 3 distinct angles. Surprisingly, chaos still prevails. Somehow, a virtually undetectable difference in the initial positions is enough to quickly send the double pendulums onto wildly different paths. This property of chaotic systems is called sensitivity to initial conditions, or more popularly, the butterfly effect. It's often captured by the image of a butterfly flapping its wings in Brazil and somehow causing a tornado in Texas. It's not all chaos though. For instance, take a look at the set of double pendulums. Even when we speed this up, they will always trail each other closely and never fall into chaos. And as you'd expect, this is true for all double pendulums released from small enough angles. But there's a twist. This is another sequence of double pendulums where, just as we did earlier, the only difference between each one and the next is a tiny increment in the initial angle of the second pendulum. By the way, we're modifying the angle of only the second pendulum to keep things simple, but you should know this still works even if you tweak only the first pendulum or both. Now, let's set it in motion. Let's speed it up. You see that? As it turns out, it's possible to find a pocket of order nestled right in the middle of chaos. It would seem there is a lurking but well-defined border that marks the territories where only order or chaos can reside. What we want then is to map out this border in its entirety. The question is, how would we even begin to do that? Well, let's start with the familiar. Let's start with order. But first, let's clear up a few things. Several assumptions underlie the double pendulums you've seen and those we have yet to encounter. First, every double pendulum consists of two weightless rigid rods, each 1 meter long, with identical 1 kilogram weights at their ends. Second, they all start from rest, with their entire movement confined to a single plane. And finally, we assume the simulations unfold in a vacuum devoid of friction or air resistance, so only gravity influences their motion, keeping the total energy constant. In the real world, if you were to set up a double pendulum on, say, a kitchen table, it would probably look and move like this. And yet this is still a computer simulation, merely the result of crunching through the equations that govern its motion. This also means that while the chaos of the double pendulum may resemble randomness, it is in fact not random. It simply obeys the laws of classical physics. Now that that's out of the way, let's dive into order. Earlier, we saw that a double pendulum released from small angles will exhibit order. To illustrate this, let's plot the angles of both pendulums as they progress over time. Okay, sure. We can see both angles periodically rise and fall. However, we can uncover a deeper pattern by looking at it from a different perspective. The key here is to plot the two angles against each other over time. Let's hit the fast forward button. Okay, and just to drive the point home, let's look at more examples of double pendulums released from small angles, along with their plots. Now, what would happen if you use much larger initial angles instead? Let's take a look. As you'd expect, their plots reveal no discernible pattern, just utter chaos. We can supercharge this visualization by noticing that for every double pendulum released from any initial position, we can make a corresponding plot of its movement, over, say, 30 seconds. Then, as we continuously tweak the initial position, we can just have the computer instantly update the plot in real time. This will help us more clearly grasp the transition from order to chaos and back. At this point, the question is practically begging to be asked. Where exactly do all of these transitions occur? Just where does order end and chaos begin? What you're looking at is a 40 by 40 grid of 1600 double pendulums. Together, they roughly represent all possible initial positions. Let's set all of them moving at once. Thanks to this, we can now broadly make out the border between double pendulums that stay in order and those that fall into chaos. The only obvious next step now is to crank up the level of detail. Currently, we're simulating only 1600, but what would this look like if we were to expand this to millions of double pendulums? Well, as you can probably guess, the challenge is figuring out how to squeeze millions into a single frame without it all just turning into a jumbled mess. This, no doubt, would be impossible. Or is it? As a warm-up, let's take another look at this grid. But this time, let's simply treat it as a map of all possible positions. This means that for any double pendulum, every snapshot of its movement would already be captured somewhere on this grid. Now here's the essential thing. Instead of depicting them as actual double pendulums, let's switch things up by representing every possible position with a unique color. The whole reason for doing this is that now, unlike before, we can significantly boost the level of detail without it turning into a visual mush. And so when we bring back the double pendulum, we can equivalently represent it as a certain color based on the current state of its angles, allowing us to dramatically cut down the size of how it's portrayed on screen, even down to a single pixel. Okay, let's apply the same transformation to the original grid of all possible initial positions. Simultaneously setting all of them in motion, we get this. Now, let's go absolutely insane by pushing my computer to its melting point. Since this video will be published in 4K resolution, we're all set to bring this 2000 by 2000 pixel grid to life, where every pixel represents one of 4 million double pendulums, each with a unique initial position. At this stage, it's worth mentioning this kind of color mapping isn't the only option. In fact, we could run this again with different color schemes, each one helping us see a different feature of the same underlying simulation. Looking more closely at the original, notice the almond-shaped region in the center? It represents a region of stability, an area where neighboring double pendulums closely follow one another, reflected here in smooth gradients, which distinctly stand apart from the static-like noise that indicates chaos. Outside the central zone, however, we can spot two other types of stable regions. First, there are these protrusions that stick out from the central area. Note that there is always a rotated counterpart for any portion because this entire diagram is rotationally symmetric, which in turn is a consequence of the double pendulum's inherent symmetry. Second, within the vast seas of chaos lie untouched scattered islands of stability. Remember this? I sampled that series of double pendulums from a slice that runs right through one of these islands, which gave us an instance of order surrounded by chaos. So what do all the double pendulums in the regions of stability have in common that the chaotic ones are missing? And how on earth did the islands of stability, above all, manage to withstand the floods of chaos? To find out, we must sift through the chaos and tease out the order hidden underneath. For this final part, let's try to pin down what causes order to unravel into chaos by closing in on one of the most bewildering spots where they collide, an island of stability. Let's also pull up the equivalent view of this visualization, the one with actual double pendulums. Did you catch that? As it turns out, for a double pendulum to exhibit chaos, one critical thing seems to need to happen first. And once it does, chaos is all but guaranteed. And that critical thing is the flip of the double pendulum. By flip, I mean the instant when either rod rotates beyond 180 degrees in either direction. Of course, it's easy to see that only double pendulums released from large angles, which we already know typically exhibit chaos, have sufficient energy to flip. So already, there is a clear intuitive link between them. But will this connection between flips and the emergence of chaos actually hold across all double pendulums? Let's find out. Once again, let's pull up this grid, but I'll slightly modify it for this visualization. I'll also bring in this tool I call a time tracker, where the numbers next to it indicate the time in seconds since the release of the double pendulums. This will determine the color to be placed on every double pendulum depending on the time it takes until the first or second pendulum flips, whichever flips first. For example, if a double pendulum flips for the first time at the 5-second mark, it will turn orange. At the 15-second mark, it will turn green, and so on. If no flips occur within the maximum time allotted for the simulation, which is 30 seconds, it will remain white. Now, just like before, let's push my computer to its boiling point by ramping this up with a 2000 by 2000 pixel grid, this time leaving out the actual double pendulums. Let's also alter the time tracker a bit by concentrating more colors toward the beginning, since most flips appear to occur early in the simulation. Let's run this again, but this time with zoomed in views of the islands of stability, and a duration of 70 seconds. Up until now, the chaotic regions appeared to be no more than a swirling, turbulent jumble. But now, they blossom into intricate patterns. And notice how the white areas wonderfully align with the stable regions we pointed out before, including the islands of stability. This makes a solid case that the border between order and chaos is the border between double pendulums that flip and those that don't. However, it isn't quite that simple. There are double pendulums that appear to fall into chaos without flipping. And taking a closer look at this other island, we find the double pendulums within it flip early on, yet they still continue to trail each other closely. All of this shows that we've only scratched the surface, and the border between order and chaos is far more intricate and fractured than we think. By now, you're probably aware that this has been more of a tourist guide than a deep technical dive into chaos theory. While the main goal was to get a series of glimpses into the emerging complexity of the double pendulum, I hope that, like me, you're leaving with a new or deeper appreciation for how powerful visualizations can be in uncovering order. It is through these visual explorations that, in the end, we might very well discover that chaos is nothing more than order yet to be understood.